This is Sam Francis, the National Programs Director. The purpose of the webinar is to acquaint you with the fire tests that have been done previously and more recently in support of mass timber building interest. And, oh, come on. There we go. So I'm going to breeze through these slides. You can read them on your PDF. This is accredited at AIA. We mentioned we didn't apply for NCSEA for this. The course description is that we're going to talk about standard fire tests and non-standard or ad hoc fire tests, specifically as relates to the interest in and development of tall wood and the Tall Wood Building Ad Hoc Committee. The learning objectives of this program are that to make you aware of and recognize the differences between those standardized and ad hoc fire tests, to make you aware of the objectives of various test protocol and the difference between them for non-standard tests, specifically ATF versus the FPRF tests, and talk a bit about E119 tests and how that's impacted the test program. Marcy, a poll, please.
Marcy, I think you're muted.
You are exactly right. So fortunately, this is self-explanatory. So go ahead and let us know what your profession is. And I've got mostly 80% have voted in 20 seconds. And since we have so much to cover, I'm going to go ahead and close and let you know that we have about 59% engineers, 24% building code officials, 3% fire code officials, 9% other, and 5% architects. So welcome to everyone that's here. We are so glad you're here. And back to you, Sam.
Thank you. Okay. The outline for this program for the next, what's left of this hour, is we'll look at fire test protocols. We'll look at mass timber compartment tests. And lastly, we'll look at how those tests impacted the ICC Tall Wood Ad Hoc fire research and how it impacted the committee and its outcome. So in concept, wood exposed to fire chars at a predictable, easily modeled rate. Wood and char both are good thermal insulators. They protect the core of an exposed wood member so that the strength and stiffness properties persist depending on the char layer, and it can be modeled. And in the figure you see, that's a three-sided exposure. Much of what we're going to talk about is a single-sided exposure, and it's different. The fire tests that I want to discuss first are standardized tests such as E84, E119, E814. And then we'll cover some compartment tests, and we'll also discuss the testing to validate the new concept of non-combustible protection. So E814, I can't even read now. E84, Steiner tunnel test, flame spread. It's a comparative test. Red oak flooring and cementitious board are used to calibrate This is, for example, products are regulated for interior finish in IBC Chapter 8, and one of the requirements is flame spread. So we'll discuss those results. E119, this is the base test to evaluate a fire resistance rating, generally measured in hours, but it could also be minutes. Fire resistance rating requirements are generally found at least the main consideration is Table 601 of the IBC and Table 602, but also other places in the code. The assembly to be tested is installed in the test apparatus in the same manner it would be installed in the field, and the test protocol specifically requires if there's a seam or a splice anticipated in the field, that must be part of the test specimen. And the North American CLT Handbook, for example, has some E119 test result values for CLT panels. Speaking of E119, AWC commissioned such a test. That particular test was 5-layer CLT, covered both sides with 1 layer of 5/8 type X gypsum. It was loaded to the maximum load the lab equipment could generate. They had never jacked it up that high. We were able to get a little over 87,000 pounds on that test specimen. There was a splice. You see a detail below. In that test specimen, failure occurred when flame appeared on the unexposed side. Here's a picture of that test specimen in the test frame, still carrying over 87,000 pounds. And if you can see here in the inset, it's not really an inset, that's the clock in the lab, 3 hours, 6 minutes, 44 seconds. And you see a bit of flame appearing on the unexposed side, which is the point of failure for that particular specimen. So there is a test report available. That's a 3-hour assembly, and you can find that report along with, and I'm about to mention the E814 testing, at our website, awc.org/tall mass timber. And much of the information we're talking about today is available at that website. So E814 is a through penetration fire stop system. It's required in several places in the code. When we did a test at Southwest Research Institute, we used panels that had been tested in a compartment test, I'll talk about in a minute, to then do E814 through penetration testing. Various piping systems and wiring systems were tested, and it was done in the 814 protocol, and those results, that test report is available on the website. I'd mention 285 because that test in Chapter 14 measures flame transmission over the outside of a building, and currently buildings are required of type 4 construction are required to pass 285. Problem is the scope of 285 is that it's to be applied to non-bearing walls on buildings of non-combustible construction. And in the case of mass timber, those exterior walls may be both bearing and non-combustible, or rather combustible. And so theoretically it's outside the scope. The Tall Wood Building ad hoc has had conversations with labs, and the labs have expressed a willingness to write reports reflecting that a particular assembly meets the requirements of 280 of the of the test without saying that it meets 285. That's a whole technical discussion about lab reports and passing tests. So how did we get here? Well, I mentioned that we did an E119 test. In the lower right here, you see what's known as a time temperature curve for E119. You'll notice that the rise in temperature within the chamber is rather slow and extends and continues to rise over a long period of time. So when we did the E119 test, there was considerable discussion about, well, yeah, but that's not very high. What really happens, so look here in the upper left, in a natural compartment fire is the temperature rises very fast to a very high level. Then as the contents of that compartment are consumed, the temperature declines as the fire enters its decay phase, and it declines over a long period of time. So there's really two different things going on here depending on whether you're looking at a compartment fire or an E119 standard time temperature curve. Marcy, a poll.
Absolutely. Which is generally true regarding typical time temperature curves of compartment fire tests versus ASTM E119 fire tests? Is it A, compartment fire temperature peaks quickly, compartment fire temperature decreases after fuel is consumed, ASTM E119 fire temperature gradually rises throughout exposure, or items A and C only, or items A, B, and C? All right, most people are voting. I'm going to give it about another 5 seconds. And I'm going to close. And Sam, we've got about 62% say that it's all three. 18% say A and C only. And 10% say C. ASTM E119 fire temp gradually rises throughout exposure. 7% say it the temperature peaks quickly, and 4% says it decreases after fuel is consumed. And Sam, I'm going to give it back to you to let people know what the real answer is.
Displayed on the screen, A, B, and C. Okay, so the outline for the rest of this program is we're going to discuss in a little more detail these fire test protocols. We'll look at the mass timber fire tests as compartment or ad hoc tests, and some discussion of the ICC Tall Wood ad hoc fire research. I mentioned that some time ago in 2015, we commissioned a compartment test from Southwest Research Institute. The compartment was 5-ply CLT, 12 by 16 feet. There were lap joint splices in the compartment, one opening in the front, which was the combined area of what one might find in an outside room, a room that had a door and a window, for example. That area was combined into a single opening to facilitate seeing what was going on inside and data collection. The test was run twice, once with CLT, cross-laminated timber panels, and once with NLT, nail laminated timber panel. The IBC currently provides for type 4 construction the requirements to produce NLT, and the test report, a video of the testing and so forth, all available at that website previously mentioned. An example here, this is the NLT floor ceiling assembly being installed on the test chamber. So here is the sequence. There's the test. The upper left is the test chamber with a single opening. The contents are typical residential furnishings of modern furnishing variety, which means it's what UL would call modern furnishings because of the higher heat content. The upper right is the test chamber at the peak of the test. You see the decay phase, and lastly, there's the chamber with all the gypsum stripped away after the contents were allowed to burn to completion. And that particular fire was about 6 meg, if I remember, 6 or 8 megawatt fire. And that, a quick word about that. Here's the E119 curve superimposed on the temperature curves from that chamber. So you see that, and these are multiple points of data collection. The actual fire rises quickly and exceeds 2,000 degrees. Within a 15-minute time, it's exceeded or reached 2,300, whereas back here on the ASTM curve, you're clear out here at about 23 minutes before you get to 1,500 degrees, and it's a long, slow curve, whereas the compartment decreases gently over time. So to continue the ad hoc tests, let me introduce Jason Smart.
Okay, thank you, Sam. Actually, first I'm going to talk about another test series that was performed by in 2017 by the Fire Protection Research Foundation, or FPRF. They commissioned a series of 6 compartment fire tests, and these tests were done for NFPA's Property Insurance Research Group, PIRG. The purpose of this test series was to collect data on the contribution of CLT elements to compartment fires for the purpose of insurance modeling. Testing was performed by the National Research of Canada, NRC, or National Research Council of Canada, I should say, NRC, at the National Institute of Science and Technology in Gaithersburg, Maryland. And all 6 of the test compartments were constructed of CLT, and they had overall dimensions of 15 feet by 30 feet, 15 feet wide by 30 feet deep. The opening on each of these structures was 6.5 feet tall by 6 feet wide on 4 of them, and 6.5 feet tall by 12 feet wide on the other 2. And they were situated on one of the 15-foot end walls. In 2 of these tests, all of the CLT surfaces were protected. So these were considered to be the baseline test because the CLT did not become involved in the fire and therefore did not contribute to the fuel load. In the other 4 tests, various CLT surfaces were exposed. And the fire performance parameters such as heat release rate, temperatures, and heat flux were measured in each test. So the contribution of the exposed CLT was then they could then determine it by subtracting the values of these parameters from the values that were measured for the baseline test. Among the findings of the FPRF test series were that CLT did not significantly contribute to the fuel load in compartments which had gypsum wallboard. I'm sorry, meant to go to the next one. There we go. Like I said, among the findings, CLT did not significantly contribute to the fuel load in compartments which had gypsum wallboard protection on all surfaces. So the ones that were protected on all CLT surfaces, CLT did not become involved and did not contribute. And for the tests in which certain CLT surfaces were left exposed or unprotected, the CLT contribution increased with increasing exposed surface area. It should be noted that the degree to which the CLT contributed was modeled by the Research Institute of Sweden, RISE, in advance of these tests. The actual test results in terms of heat release rate and temperature were very close to the model predictions. So that showed that the contribution of CLT, exposed CLT, I should say, in a compartment fire can certainly be modeled accurately. Switching to another test series, In the fall of 2017, AWC commissioned a series of tests that was intended to validate the protection contribution values that are assigned to non-combustible protection. Three of these tests, or three fire tests, were performed on CLT floor ceiling assemblies with varying amounts of non-combustible protection. In this case, the non-combustible protection consisted of varying layers of 5/8" Type X gypsum wallboard. One of these tests was an unprotected control test in which the CLT floor ceiling assembly was fully exposed. The results of this test were used to establish the baseline of fire resistance for the CLT alone. In each test, the series were subjected to a standard E119 time temperature exposure, and they were loaded all to the same level. Also, each assembly consisted of the same CLT grade, manufacturer, and thickness. So this made it possible to directly determine the contribution of the protection from the non-combustible protection, the protection of the gypsum wallboard. This graph shows three plots of center point deflection versus time within the E119 furnace. And the red curve on the left shows that of the unprotected control assembly. The blue curve that's in the middle is from the assembly having one layer of 5/8" Type X protection, and the green curve on the right is from the assembly having three layers of Type X, 5/8" Type X gypsum wallboard protection. As you can see, each of these curves follows a similar path, with the exception that they're offset from one another by time shifts that are equivalent to the additional time to failure attributed to the non-combustible protection that was applied over them. This time shift amounted to approximately 41 minutes for a single layer and 127 minutes for three layers. In other words, about 42 minutes, an average of 42 minutes per layer for the three-layer one. Each test was carried out to the point of imminent structural failure, which consistently corresponded to a center point deflection of about 12 inches. And then this table summarizes some of the specifics regarding the CLT type, dimensions, applied load, and non-combustible protection that was used in each test. The only variable, like I said, was the non-combustible protection. Everything else about these assemblies was identical, including the loading. By subtracting the measured time to failure of the unprotected CLT control from those of the protected assemblies, it was possible to directly determine the additional fire resistance from the contribution from the non-combustible protection. You can see here from this analysis that the 5/8" Type X protection consistently provided between 41 and 42 minutes per layer. This is shown in the bottom row here. Therefore, the results of this test series, taken in combination with other test series performed previously, validate and justify the assigned contribution values of non-combustible protection applied to mass timber assemblies. And now I think Marcy was going to ask a poll question.
I am indeed, and I have the wrong one. Okay. I'm sorry, this does not line up to, I think mine just looks different than yours does. Yes.
Do you want me to
Sorry.
read? Oh, okay.
No, I'm good. It's just what I have doesn't look like the one on the screen. So it's all good. Sorry. Standardized fire tests show that each layer of 5/8" Type X gypsum wallboard increases mass timber assembly fire resistance by at least 20 minutes, at least 25 minutes, 30 minutes, 40 minutes, or 60 minutes. Go ahead and vote. People are voting quickly. I like that. Thank you. And I'm going to go ahead and close. And we have 71% say at least 40 minutes, 13% at least 30, 12% at least 60, and just a few people at least 20 and at least 25. All right. And Jason, what is the real answer?
Well, that's good to see because the correct answer is 40 minutes. So the vast majority of people got it right. 40 minutes per layer of 5/8" Type X gypsum wallboard.
Perfect.
So now Sam, I think, was going to start us off on the next segment of this presentation.
The next and last of the three sections, the Tall Wood ad hoc fire research. And while And while I'm remembering how to advance this, I'll mention that that 40 minutes, if you go back and look at those curves, is a conservative number. Okay, so back in 2015, the ICC Board of Directors appointed an ad hoc committee on tall wood buildings, specifically charging the TWB to explore the building science of tall wood buildings. And depending on the outcome of that research, to investigate the feasibility of, and if warranted, take action on developing code change proposals for tall wood buildings. All of that was to be further refined by the committee. That ad hoc committee consisted of representatives from building construction materials, which would include steel, masonry, wood, and gypsum, building and fire officials, architects and engineers, including fire protection engineers, fire protection or fire science experts and researchers, and other related stakeholders. We met a bunch of times, and in between those meetings, there were literally dozens and dozens of webinar style conference calls to work through all of these issues. You'll notice at the bottom, the Tall Wood Building Ad Hoc identified 82 major issues, not little things, major issues to work through. That's why the committee went on for a couple of years, and it's why I feel older at this moment. So one of the things that came out of that, there was a fire work group appointed by the chairman of TWB, and that fire work group created the test protocol for a test to be conducted to look at the concepts that TWB had heard about and considered. The purpose of that, of the test protocol, among other things, was to evaluate occupant and firefighter tenability for the purpose of egress in terms of occupants, suppression efforts in terms of firefighters. And that dictated, by the way, the configuration of the test assembly, all of which the TWB deemed to be important to the further development of codes and standards. It was conducted at a U.S. government facility, namely alcohol, tobacco, firearms, and explosives. They've added that to their title, still call themselves ATF. And it was all supervised by the U.S. Forest Products Lab staff. So let me turn it over to Jason to talk about the particulars of the test.
Okay, thanks, Sam. Just to give some of the specifics of the mass timber test building that was constructed for the ATF full-scale building tests, the floor plan simulated a multi-story condo configuration. And as Sam has noted previously, it's very realistic because he could have sworn he stayed in that exact same building last time he was in a suite or hotel. So the building was constructed with 2 stories because that was deemed sufficient to simulate multiple stories for the purpose of data collection. The interior dimensions of the simulated apartment or condo on each level was 30 feet by 30 feet, the interior dimensions. That's 900 square feet on each level. The building was also included a corridor and stair shaft to the exterior of the apartments on each level, such that the overall footprint of the building was about 37 feet by 46 feet. The general floor plan for the first level is shown here in this figure, and the floor plan for the second level was the same. The TWB fire work group, which Sam just mentioned, specified a target fuel load of 550 megajoules per square meter. This value, which I'll talk about a little more later, it corresponds to the mean fuel load plus 1 standard deviation based on a survey of typical Group R occupancies. 5 fire tests were performed. 5 fire tests were performed in the structure. The first 3 represented unlikely scenarios in which the automatic fire sprinklers, which are mandated by code, completely fail to activate and the fire service is unable to respond throughout the duration of the fire. So that represents a pretty unlikely scenario for both of those events to happen for the same event. In ATF test 1, all of the mass timber surfaces within the test structure were protected with 2 layers of 5/8 inch Type X gypsum wallboard. Since the mass timber surfaces did not contribute to the fire on this particular test, it served as a baseline to which subsequent tests could be compared. In ATF test 2, 30% of the ceiling area was exposed in the living room and the bedroom. In test 3, the CLT walls were exposed in the living room and the bedroom. Test 4 had code-compliant automatic fire sprinkler system, and in test 5, which also had sprinklers, the sprinklers were purposefully deactivated so that they wouldn't activate automatically, but rather they were manually charged after a 20-minute delay, 20 minutes after a point which I'll describe later, in order to simulate the manual charging by the fire service at the fire department connection. In both tests 4 and 5, all mass timber surfaces were exposed in both the living room and the bedroom. The right column of this table shows a duration. I just wanted to point to that real quick because you can see that in test 1, where all the mass timber surfaces were protected, it went for 3 hours. And by that time, all the furnishings and other contents were completely consumed. Tests 2 and 3 were allowed to go for an additional hour beyond that, until 4 hours, so that it could be verified that no fire regrowth would take place. The image on the right side of this slide is a rendering from the CAD drawings depicting how the structure was assembled with individual CLT panels and glulam members for columns and beams. All of the CLT used in the structure was 5-ply with 1 3/8 inch thick Doug fir larch laminations. The laminations were bonded together with a polyurethane adhesive, and the total thickness of the CLT panels was 6 7/8 inches. The non-load-bearing unrated partitions between the individual rooms within each apartment were constructed of steel studs with 1/2 inch regular gypsum on each side. As you'll see in some of the pictures that will be on the following slides, these unrated partitions fell away fairly early on in the test. This was by design and fully expected, since the partitions were not designed to be fire resistance rated, and they wouldn't be required to be such in the per the code. So for most of the duration of the test, in the 3 long tests, tests 1, 2, and 3, the apartment was like a single large compartment with an area of 900 square feet surrounded by CLT walls and a CLT ceiling. On each level, the door between each apartment and the corridor had a 20-minute rating, and the door separating the corridors from the stairs stair shaft had a 90-minute rating, as would be required by code. As I mentioned, the TWB Ad Hoc Committee specified a fuel load of 550 megajoules per square meter, but the actual calculated fuel load that we calculated of all the contents that were present in the actual tests, when you include all the furnishings and other combustible contents, was actually closer to 570 megajoules. So it was certainly very close, but it was actually a little bit beyond what was specified, even more than what was specified by the TWB Ad Hoc Committee. A good portion of this fuel load was achieved through a combination of typical residential furnishings, combustible floor coverings, cabinetry, and other combustible contents. Even with all of these furnishings and contents, it was still necessary to add additional fuel load in order to achieve the specified fuel load. This is because the specified fuel load was 1 whole standard deviation above the average, like I said, for Group R occupancies. Thus, in order to make up the difference, wood cribs were also added within the test structure for each test. Here's a compilation of photos showing the interior of the bedroom and bathroom, courtesy of the U.S. Forest Products Lab and ATF. And a lot of the photos and video that we'll be showing is courtesy of ATF and the U.S. Forest Products Lab. The photo on the right and the one on the bottom center show some of the combustible fuel load that was present in the bedroom in each test. The rest of the photos were taken prior to the placement of these combustible items. And these photos show the interior of the kitchen and the living room. The top center photo shows the cabinetry which was installed in the kitchen. The bottom right and bottom center photos show some of the combustible fuel load that was present within the living room in each test. And the rest of these photos, again, were taken prior to placement of furnishings and contents. Note, by the way, the exposed portions of CLT on the ceiling, visible in 3 of these photos. So you can tell that these photos were taken prior to test 2 on the second level. Going through each of the ATF tests individually, let's first take a look at test 1. As I said, in test 1, all of the mass timber surfaces were protected. The photo on the lower left was taken after the mass timber construction had been completed and protected, but before completion of the non-load-bearing unrated interior partitions. The 2 photos on the right show the furnished living room and bedroom just prior to the test number 1. Now let's watch a video. Sam, will you cue that up? This is test 1. And like I said, the individual video feeds shown in this clip are recorded and compiled by ATF and FPL, so thanks to them. And also note that this is being played at a greatly accelerated rate. You can see the clock on the lower left corner there. At some points it'll be times 32 speed. Flashover occurred in the living room at around 13.5 minutes, and then it occurred in the bedroom at around 17.5 minutes. In general, flashover is the point at which all exposed combustible surfaces within a given room suddenly become involved in the fire. That's the general definition. For the purposes of consistency for evaluation in this particular test series, time to flashover was taken as the point at which the average temperature of 2 particular thermocouples within either the living room or the bedroom reached 600 degrees Celsius or 1,110 degrees Fahrenheit. So you can see the at this point we're just about to start the decay phase here. It's still a very intense fire at this point, though. Actually, I'm sorry. This is still in the very most intense portion.
I didn't unmute myself, I think.
You can see the fire from as seen from the corridor there. This is 45 minutes into the test. And there goes the door. It fell in at right around 1 hour. By the way, this, as I said earlier, this is a 20-minute rated door, so that's certainly good performance. No flaming on the backside occurred until around 27 to about a half an hour into the test.
I'm sorry, Jason, I had muted myself, and I wanted to point out that not only that was a 20-minute door, but in that video, you could have noticed the instrumentation in the corridor that we did in order to gather data to measure tenability in that area.
Yes, thanks. That is definitely one of the findings from this test series. You can go to the next slide, and I'll talk about. I'll show some of the still shots that were taken at various stages. So as you can see here, we have one shot of ignition, not much to see there, some flashover shots, and then decay phase. The bottom center and bottom right photos show the condition of the living room and kitchen and also the bedroom following the test. Note that all of the combustible contents and unrated partitions are gone, but the structural elements are essentially unaffected. The mass timber elements did not become involved or contribute to the fire in test 1 because they were protected. Just as was done for the FPRF test series, the Research Institute of Sweden, RISE, also performed modeling predictions for this ATF full-scale building series. The graph here shows how closely the modeling predictions were to actual measurements for heat release rate in test 1. The model slightly under-predicted peak heat release rate, but it was followed very closely for the remainder of the test, and the area under the curve was essentially the same for both. Of course, test 1 was carried out to 3 full hours, but this graph only shows the first 2 hours since heat release rate values were so low in the 3rd hour. The fire had almost completely self-extinguished by the end of the test. In test 2, 30% of the CLT ceiling areas in the living room and bedroom were left exposed, and this amounted to 20% of the overall ceiling area throughout the apartment. If you look at the overall ceiling area of the 900 square feet, 900 square foot apartment. The photos at the bottom of this slide show the exposed ceiling areas, and in both test 2 and 3, a load was applied to the floor ceiling assembly above by using large barrels filled with 130 gallons of water each. Now let's see a video of test 2, Sam. So again, test 2 was on the 2nd level. As you can see there in the upper left corner, that image shows the entire structure. Flashover occurred at around 12 minutes in the bedroom, in the living room, and in the bedroom it occurred again at 17.5 minutes approximately. So it was very consistent there, especially for flashover in the bedroom. And you can see in the upper right corner how the bedroom is just about to flash over there. And the right center photo there is a close-up. It was from a camera within the bedroom. You can see the polyethylene plastic sheet over the bed, over the mattresses, and you see it start to smoke now. It's starting to off gas, and they start to flame any second now. And that pretty much corresponds with flashover in the bedroom. There it is. Again, as Sam pointed out, the lower right corner shows the infrared imagery, so it shows heat. And then the lower left photos show the corridor and the stairwell. Towards the end of the decay phase, there was no significant flaming on the exposed CLT areas on the ceiling. You can also see the condition of the exposed CLT areas at the end of the test. The exposed CLT surfaces had self-extinguished by the end of the 4-hour test. So if you'll advance to the next slide, Sam, we'll see some, again, a compilation of still shots at various stages of test 2. Go back 1, I think. The photos on the bottom right of this, well, that's okay. Don't worry about it. We'll look at this one because this shows the same thing. The photo shows the condition of the CLT following test 2 after removal of the gypsum wallboard. You can note that the areas protected with 2 layers of 5/8" Type X gypsum wallboard were uncharred, except for a few minor localized surface charring in limited spots. You can see down near the floor, one little spot like that. The exposed CLT surfaces self-extinguished during the decay phase. And let's see, let's go to the next slide. The next slide also shows a shot that was taken around that same time, right after test 2, after the gypsum was removed following test 2. And again, the areas protected with gypsum wallboard were uncharred. Here you can see not only the CLT ceiling, but also the glulam columns and beams after removal of the gypsum. And again, no major charring, just some limited charring like the lower edges of the glulam beam there. Here's a photo of a sample cross-section that was cut out of the exposed CLT ceiling following test 2. So it was from the ceiling, exposed area of the ceiling. It clearly shows the protective layer of char on the first lamination. And this photo shows another sample cross-section, which was also taken from the exposed ceiling following test 2. On this sample, the char has been scraped off, though, in order to more clearly show the depth of the char. As you can see, the char was not quite 1 lamination thick in this location. It was about 1.25 inches deep. The reason a portion of the lower lamination was not charred is because this cross-section was cut in a manner such that it spanned a portion of a protected area and then also a portion of a exposed area. So you can see the transition of the char depth going from exposed area to a protected area. Just as for test 1, ATF test 1, the modeling predictions were very close to the actual measurements. This model was able to accurately account for the additional heat release rate from the exposed CLT ceilings. Although this graph only shows the first 2 hours, again, it was actually carried out the test was actually carried out for 4 hours. As you can see, the fire was well on its way to self-extinguishment even at the 2-hour mark, and there was no fire regrowth observed throughout the test. So moving on to test 3, there were 2 parallel walls, opposing CLT walls that were exposed, one in the bedroom, the other in the living room. These are identified on this diagram, which you saw earlier also, as wall D in the bedroom and wall B in the living room. At the beginning of the test, there was a partition wall between them. Like I said earlier, however, this was not present throughout the majority of the test because it was unrated, it fell away. Now let's watch a quick video of test 3.
We didn't mention in the previous 2 tests, it's true for all 5 fire tests. While there are no appliances in the kitchen, pipe penetrations from the floor below and pipe, just as it would be plumbed up in a real apartment, existed there, and they were of course treated with E814 required systems. The ICC Ad Hoc Committee was insistent that this test structure be compliant other than the mass timber, because no such code requirements exist, be compliant with existing requirements. That's why we have down here in the lower left a 90-minute door in the stairwell, and next to it is the video of the 20-minute door in the apartment. And in this test, you can see the instrumentation cabling on that wall and on the wall across the way. Just for comparison, while we're watching this big fire, remember the test at the single compartment test was about 6 megawatts. The peak on this was about 23 megawatts. That's a big fire.
All right, so I'll take it back and talk a little bit about, just to wrap it up for test 3, here's the graph for test 3 of heat release rate showing both the predicted and the measured values. The fit between the measured and predicted curves, again, is it's very good. In fact, it's actually better for test 3 than it was for tests 1 and 2, despite the fact that test 3 had more CLT exposed than the others. So let's talk about test 4. As you know, the code would require that buildings of this type be protected with an automatic fire sprinkler system, in addition to gypsum protection requirements. Test 4 was a test to investigate how sprinklers would perform in a mass timber building, even if non-combustible protection were not used. All mass timber surfaces were left exposed in both the living room and the bedroom. This included exposed CLT walls, CLT ceilings, and glulam beams and columns. The picture on the lower right shows the extent of damage after the test. The fire was limited, as you can see, to the first item ignited, which was just one of the lower kitchen cabinets. Let's watch a video of test 4. And I wanted to mention that in tests 4 and 5, in addition to one difference being that while test 4 had automatic sprinklers, both of tests 4 and 5 also had glazing over the openings, as this was to simulate an actual building. This was necessary also in order to ensure that the sprinklers would activate in approximately the same amount of time as they would in an actual apartment. The sprinklers activated automatically at 2 minutes and 37 seconds, and it quickly suppressed the fire after that. You'll see it very soon in this image. There it is, just growing within the kitchen cabinet, the lower cabinet where it was ignited. And as soon as the sprinklers come on, which is just happened, it pretty much douses it. And we probably don't need to watch the rest of that video because it's just steam. Obviously, there was no fire regrowth after that. So let's see. I'm sorry, go back one. Let me introduce test 5, which was the last of the tests. Test 5, just like for test 4, all mass timber surfaces were fully exposed in both the bedroom and the living room. And the sprinklers were purposefully prevented from being automatically activating. As I said earlier, this was, and then they were charged 20 minutes after the time at which the automatic sprinklers activated in test 4. So basically 23 minutes into the test. This simulated a scenario in which the sprinklers failed to activate automatically, but then are charged manually by the fire department upon their arrival at the scene. Let's watch a video of that now.
While we're watching this video advance, I'll mention that these videos are all available. You can watch them at your leisure. Go to the website awc.org/tall mass buildings, and under fire tests, you'll see these available so you can watch them. And you'll notice that I've manually advanced this for the sake of time on each of these fire test videos. And while I was talking, I failed to point out that the ATF firefighter went up and using a pike pole knocked out that glazing to add to the ventilation in order to expedite the intensity of that fire. As a result, both the living room and the bedroom were about flashover point.
Yep.
The kitchen flashed over. And now we're just watching lots of steam from from the system. You notice it's 24 minutes. The sprinklers went off at 23 and some change.
So despite the fact that flashover conditions were reached in the kitchen and nearly reached in the bedroom, the sprinkler system effectively suppressed the fire upon being manually charged, even though it was a delayed activation. Now I think Marcy, if we'll go, well, we can, I don't know if we need to watch the rest of this, but Marcy has a poll question coming up also.
There we go. I have to advance all the way to the end to get out of that.
Okay, so in unlikely scenarios where sprinklers fail auto activation but fire service charge manually, ATF test 5 showed sprinklers did not control exposed mass timber fire, or sprinklers did not stop fire intensity due to flashover, or sprinklers suppressed exposed mass timber fire, or items A and B. So go ahead. It looks like 30% of you have voted. Keep going. I'm going to give about another 5 seconds. I know we're plowing through these really fast, but we've got a lot of information. All right. So it looks like 76% say C, sprinklers suppressed the exposed mass timber fire, and 21% say items A and B, it did not control and did not stop. So let's see what the real answer is.
Thanks, Marcy. Once again, the majority of respondents did get the answer correct. It is C. Sprinklers effectively suppress the fire despite 100% mass timber exposure in both rooms. Okay, so I'll talk briefly here just to sum up, give some of the times at which key events occurred and comparing between the ATF tests, the 5 different tests. As you can see, for each test, flashover in the living room was fairly consistent, at least for tests 1 through 3. It was consistent at around 12 or 13 minutes after ignition in the living room, and very consistent at pretty much 17 minutes for the bedroom, despite the differences in exposed mass timber areas for each of these tests. It was a very consistent time to flashover. The time that it took for flames to breach the 20-minute rated door into the hallway was about 27 minutes and 30 minutes respectively for tests 1 and 2. In test 3, flaming on the backside of the door of the 20-minute rated door occurred early because the door was actually not sized properly. But in any event, the flames did not spread beyond the door within the corridor. That was evident in the first 3 videos that we saw. And just to sum up, lastly, I wanted to mention some of the other important findings from the ATF tests. Analysis of the ATF test results have shown that exposed CLT did not have a significant impact on the outcome of the event, the overall outcome anyway. The fires eventually burned out in all cases, or they were suppressed by sprinklers in the last 2 tests, of course. And in all cases, the structure was left intact. Penetration fire stops compliant with ASTM E814 prevented the spread of fire beyond the compartment of origin. That's one thing I didn't mention earlier, that there were some penetration fire stops installed in the test structure, and they were able to contain the fire. And tenable conditions were maintained in the exit corridor and the stairs for more than sufficient time to allow safe egress of occupants. And then also conditions that were tenable for firefighters were maintained in both the corridor and the exit stair shaft throughout the entire test duration.
Before we leave this slide, Jason, I want to add that the tenability was estimated by professionals, and it was done when the Tall Wood Building Ad Hoc Committee was considering 20 stories as a allowable height, and that has subsequently been reduced to 18 stories in the current submittal. It's a conservative approach, but the tenable conditions were maintained.
How connections fared during these tests? I know we didn't cover that specifically, but that's an important part of this.
Sure, in the planning of the fire tests at ATF, the Tall Wood Ad Hoc Structural Committee, structural work group, requested of the fire work group that a number of different kinds of connections be created and implemented within that test. I'll let Jason handle the details of it, but a number of connections were present and instrumented to measure their performance.
Yeah, that's right. Because the TWB gave guidance on the various types of connections they'd like to see, the test structure, the ATF test structure, did have a wide variety. We were able to incorporate quite a few, or I should say FPL and ATF were able to incorporate quite a few through the construction firm Lend-Lease that was doing the construction work. So it worked out well, and all of the connections were designed with protection that complies with Chapter 16 of the NDS, specifically Section 16.3. So they were fully protected, and because of that, none of the connections really received any major charring, or they were fully protected as would be required by code. They were instrumented, as Sam noted, and with thermocouples specifically. And the thermocouples told the same story that the visual told after the test was over, and namely that the temperatures no elevated temperatures were measured, with the exception of one anomaly that happened to occur at a spot where, due to there was not sufficient sealant at one particular location, and some hot gases passed through there. But that was not indicative of a general charring on that connection. That was on a ledger. Yeah, the connections were protected, and they performed well as such.
Excellent. A couple of questions came in. Sam, maybe you can address this one about that door that was improperly installed and maybe prematurely led to some issues.
Well, it's not fair to say the door was improperly installed. It just happened to be the wrong size door, and therefore it couldn't be properly installed, if you'll forgive the expression. This is the problem with working under such an accelerated timeline. You just don't have time to chase down everything if something goes wrong. The impact of that door, it was, if I remember, and I'm getting old and don't always remember correctly, but I recall that was an 11-inch deep frame, and if you all will remember Jason telling you that this was a 6.5-inch thick wall, so an 11-inch frame and a 6.5-inch wall doesn't work. It was packed out. A number of things were done. So let's just say it was installed differently, and it didn't last as long as the other two, which were correctly sized. And from a personal observation, the 20-minute doors went, well, the door physically failed at 58 minutes. That's a 20-minute door. Kudos to Gus Degenkolb and his group back when they created the door and opening protective tests that we utilize and depend upon now. This is, in my mind, is a clear indication that they're successful, and I would reiterate that corridor was instrumented so we could know if tenable conditions existed. But the answer to the the question about the door is that it was just the wrong size and there's no way to properly install it. This was not a worker error.
All right, thanks. While we're on the subject of doors, remind us again, why was that door left open in test number 5?
I can answer that if you want me to, Sam. The reason for that is because, as you recall, in both tests 4 and 5, the openings were glazed as to make it as realistic as possible, because that's the way the openings would be in an actual structure. We ran some calculations and simulations and realized that the fire would not, it would smother itself. Basically, it would run out of oxygen, and it never would go anywhere if it didn't have some additional air supply. So despite the fact that these doors, these 20-minute rated doors, are self-closing, and so it's not really realistic to prop it open, because in reality they would be closed in a fire event. That's the whole point of a self-closing door. We went ahead and propped it open just to make it so that the test was a little more eventful and it actually went somewhere, so that the fire would actually grow. Otherwise, it would not have grown. It would have smothered itself. Sam, do you have anything to add to that?
Well, yes, I'm a dissenter. I believe the fire would have grown. It just would have taken a long time, and you guys wanted to go home.
All right. Talk a little bit about the sprinkler system. What is it, NFPA 13 or 13R?
It was an NFPA 13 compliant system, or design in accordance with NFPA 13. And but however, the design was actually conservatively done for light hazard. So it was low density coverage. That was the design, and that was done because basically that means it can be considered applicable to other designs of higher density. Yeah.
And one last question as we wrap up here today: how many buildings did we actually construct for these 5 tests?
Only one building was constructed. It was the same building that was used for all 5 of the tests. Like I said, the structure remained intact for every test. Now, there were some panels that were replaced only after test 2. Some of the ceiling panels on the ceiling panels only 2 of the CLT ceiling panels, the ones which were exposed, were replaced. The rest of them did not need to be replaced. So that's the only major renovation that was done. And then there were some other minor touch-ups that were done to the localized areas of minor charring that you saw in some of the pictures. That they would just finish that off so that it would accept a screw for attachment of the next of the drywall for the next test, the test following that. Sam, did you want to add anything else to that? Or?
No, simply that panels were replaced. The building was repaired and rehabilitated when it was necessary. And certainly you saw photographs of that ceiling section. That, by the way, was the same piece of timber in both photographs. We had taken that piece of panel out and replaced it with new panel, and then sliced it so that I took those photographs. That's why I apologize for the quality. One was at a weird angle, but at any rate, that's all that was done. One building.
Well, thank you both for an excellent presentation. That'll wrap it for today. Again, I'll direct you to our website, awc.org/tallmasttimber, for copies of the test report. And you should have by now gotten links for copies of the PDF for today's presentation, which also contains a lot of this information. So hope to see you back next week for the part 2 of this series next Friday on adhesives. Have a great day.